And the next question that we asked is, when you see these supermassive black holes. Supermassive black holes are basically the ones that you see in the center of any galaxy. In our case, it is Sagittarius 2A in our Milky Way. So let us consider this as the time scale. This is where the universe started, marked as 0. And this is where we are now, the contemporary universe. 13.8 billion years has happened. So we see these big supermassive black holes which are at the center of every galaxy, and these are like 4 million, equivalent to 4 million solar mass, which is the Milky Way case. It could be millions and billions of solar masses in case of bigger galaxies. So the general idea was that you start with nebular gas in the beginning, then these stars are formed, and these stars die and they lead to black holes because of, let's say, supernova. So you have these black holes here, and these black holes keep feeding the mass near it, which could be stellar gas, could be stars, planets, or similar black holes. And over a period of time, they become so huge that they are millions of solar masses of equivalent. So this was the general understanding. But so when they try to look back, so now you have a supermassive black hole in the contemporary universe. So they thought that when you look back in the past towards the early universe, you should not see a supermassive black hole. You should see a small black hole forming, and then over a period of time it becomes supermassive. But exactly the evidence was contrary. What they found was supermassive black holes were already formed in the early universe itself. So it was contradictory. How is it possible that black holes, generally they start with star dying, black hole feeding, and then becoming supermassive black hole? But what we see now is it is taking a shortcut. The early star itself is converting into a supermassive black hole. So we need to find out how is that possible. Just to summarize a bit about how a black hole is formed. So when a star dies, from a nebula you have star forming, and based on different masses of solar mass of the star, when the star dies in a supernova, it could either be forming into a dwarf star, neutron star, or a black hole. Less than 1.4 equivalent solar masses, it will end up as a dwarf star. Between 1.4 and 2 solar masses, it is a neutron star. Beyond 2 solar masses, it has to be a black hole. So black hole, if you see the smallest black hole you would see is equivalent to a 2 solar mass. Now, as we said, these keep feeding and mergers of black holes and becomes a supermassive black hole as seen at the galactic center. And what they found is supermassive black hole in the early universe, which means the birth of a supermassive black hole was not from stellar gas to star to a supermassive black hole. From the stellar mass itself, the supermassive black hole took a shortcut to form. Now, to understand that, you need to study a bit about how stars and galaxies are formed. The classical model of universe is where you have, which is based on gravity, is what you know as the normal physics of it. Suggests that it starts with just a stellar mass, a nebula. This is just a globule of gas, so to say. This, in turn, through gravitational coagulation. What I mean by gravitational coagulation is the gas itself is collapsing onto each other because of the gravity, and that leads to stars and planets, the planetary system, and the galaxies themselves. As you can see, it looks very outlandish for just a gas a globule of gas to form into stars and planets like this, or for that matter a complex structure like a spiral galaxy. So I will show you a few aberrations, explain you a few aberrations as to why this gravitational coagulation does not sound very sound explanation for formation of star and galaxies, and we just don't hit and run away. We suggest an alternative model of universe in Manthan, wherein we suggest how could, if not for gravity, how could these stars and galaxies would have formed, again from the same system, from the globular gas. Now let us look at these aberrations. We know through common sense that if you have a system to begin with, start with, and then you want to convert it into another system, obviously there will have to be an external force acting on these. In case of gravitational coagulation, it is gravity. Now, it's a cause and effect. If the cause is strong, the result is also equally strong. If the cause is weak, the result is also weak. So we are applying gravitational coagulation here, which is uniform and weak force. So how can you expect, if you start with a spherical globe of gas and you apply gravity, all you can get is another smaller globe, maybe spherical in nature again. But to believe that you will apply this weak force to a spherical globe and you end up with a flat structure, because these are all flat structure. From a globe, you are getting a flat structure. It doesn't work that way. And the second thing is, if you have a spherical thing and you want to have a flat structure, the external force has to be a disruptive in nature. It has to have this rotational energy, because that rotational energy is what is going to collapse this globular structure because of strain centrifugal force to make it into a flat structure. And this is not what we are seeing here. Gravity only works in one direction, whereas it is not disruptive and it does not create a rotational energy. And let us assume, for the sake of argument, that this gravitational coagulation weak force is giving you a rotational energy, some kind, all of them coming together, and the star gets heated up and it starts rotating, and then it makes flat. What does that mean? That means first star was formed. When I say star, it is the central form. In case of galaxy, it is the black hole or the supermassive black hole at the center. That started, the star started, and then the planets came into being. But what we see is stars and planets start forming simultaneously. So these are the three aberrations which does not suggest that gravitational coagulation may not be the reason why these globe of gas got converted into planetary system or complex galaxies. As we said, we are not going to hit and run. So what is it that we are going to suggest in alternate model of universe? Okay, classical model of universe you have, and you start with nebula. Alternate model of universe is Manthan. You both start with nebula. Here we are saying that there is gravity acting on the gas and it is collapsing into a star. What we are suggesting is, if and if only we could have an ionized charge, because nebula is basically a gas. If we could have an ionized charge, these ionized charges are basically the jump from a higher density to lower density, higher density of charge to a lower density of charge. That could kind of give you a perfect source of kinetic energy, and you will be able to create a disruptive force. But there is a challenge here. The source of the ionized charge is the nebula itself, and these nebulae are very, very cold. Agreed, it's gas. Whether it is present contemporary universe or the ancient universe, that nebulae is basically a cold gas. In case of ancient universe or early universe, it was hydrogen gas, and hydrogen gas boiling point is minus 253 degrees centigrade, just a few 20 Kelvin above the absolute zero. So though it is in the form of gas, it is very, very cold. And for you to have ionization, the temperatures which are required is 10,000 Kelvin. So how will you bridge this gap from minus 253 to 10,000 Kelvin? In case of contemporary universe, it is possible because near the nebulae, there are always the stars which have already formed, because we are talking about contemporary universe. Those stars, when they die, there is supernova, and it compresses. When the supernova is an explosion, it compresses the other gas, and that becomes hot to the extent of 10,000 Kelvin, and ionization is possible. But when we are talking about early universe, ancient universe, there is no star, just gas. So there is no supernova to help it reach that 10,000 Kelvin. But what helps us to theorize is the contemporary universe that we see is 13.8 billion years after the Big Bang. The universe has been expanding and at a greater acceleration. So what we have is a universe which is expanded to has been expanding for 13.8 billion years. Now convert all the mass that you have, all the stars, all the planets, all the galaxies, you convert that into hydrogen gas, hypothetically. Now start going back in time. So that means the universe is collapsing. So if you imagine all this mass, gas in a small box, the volume of this box is decreasing. Now take it back to as close as, let's say, 0.1 billion years. 100 million years, just when the Big Bang was, just a little after that. That means the volume is reducing to a great extent, but the mass remains the same, and mass has nowhere to go, and hence the temperature would have increased. When that temperature increases, obviously it will be more than 10,000 Kelvin. That would give a conducive atmosphere for the nebulae to have ionization. Agreed. Now we have taken care of the challenge of that early universe had nebulae where the gas was in ionized condition. But how does ionization lead to a supermassive black hole? We will address one by one, step by step. So let's say you have a nebulae. This is early universe. No stars formed, just a gas. Hot gas, ionized gas. So as I said, the nature of ionization is that these are highly charged particles and they are always moving from high density to lower density. So obviously in this gas, when it is ionized, there will be all kinds of movement of the charge. If it is haphazard, nothing happens. But imagine if these charges are aligned, there is a chance that it could be cumulative. When two charges are aligned, it could be cumulative. It is like making a rope out of threads. So when you have such huge charges aligned and moving from higher density to lower density, they have an inertia also. They have the inertia to move the mass along with them. So when you are moving the mass along with it, it is giving you that rotational energy, that disruptive force that we were always looking for. Now what happens to this charge? What option does it have? See, this charge that we are showing here, it's starting from here. Obviously it will come to the end. When it comes to the end, there is no mass beyond that for it to jump or to move. So it will be forced to change its direction along the surface of this globular mass. And when that happens, that is like moving the gas in an elliptical form. So obviously it keeps changing direction in the edges and then it has to come back to where it started possibly. So you try and understand, it is becoming a more of an elliptical nature. So what we have is possibly a structure leading to a galaxy. And what about the star? See, all these cumulative charges which are moving from high density to the lower density, it need not be all of them are going to the end of the globule, there could be small gaps in between. So it will be forced. It can't jump that gap. There is mass beyond that, but there is a gap. So it won't be able to jump. So it turns there itself. That becomes a small globule of Mars, which becomes the seed for a star. So that is how these galaxies form. Now, our intention is not the whole entire galaxy itself. If you want to understand how the spiral arms formed, the barred structure of galaxies, you can see my early videos. You will get an idea of it. For now, we will just concentrate on the central bulge, because that is where we are interested to go to the supermassive black holes. We are trying to see that this globule itself can directly take a shortcut to become a supermassive black hole, rather than forming star and then feeding and merging and becoming a supermassive black hole. So look at what is happening in the central bulge. This central bulge also, it is the same way. You have the charge which are aligned, they are cumulative in nature and they are having momentum, and it is changing direction when it reaches the edge of the globule, and it is leading to that structure of the bulge. And again, this bulge, just the way we talked about how the stars are formed, there could be stars forming inside the bulge. Now, imagine a situation wherein the center of this bulge, since it is in the center, the chances are that it is uniformly dense, that part of the bulge. And we are not looking at this complete bulge, entire mass of this bulge converting to a supermassive black hole. What we want is just a partial bulge. You will know that the mass ratio between the supermassive black hole at the center, Sagittarius 2a, it's 4 million equivalent solar masses to 100 to 400 billion solar masses. In the sense, the ratio is 1:25,000 or 100,000. So in the sense, you are not looking at the complete mass to be converted into a star. What you are looking for is 1 divided by 25,000 of this star, and possibly the central gas. Where there are no gaps, there is a small amount. That small is as small as or as big as 4 million equivalent solar masses. Now that, imagine what is happening to that partial bulge. Again, the moving mass hits the end. There are no gaps. We are saying it is uniformly dense. So the change of direction happens, and this leads to a structure of the bulge itself. Dense mass, which is equivalent to 4 million or billions of equivalent solar masses, that becomes the seed of this humongous star that we are talking about. And that humongous star would take a shortcut to become a supermassive black hole. And that is how supermassive black holes are formed along with the galaxy. In the sense, there are galaxies, spiral arms, barred structure, everything is forming, but the center of the bulge happens to, because of the ionization that we talked about, you get a chance to form a supermassive star, which acts as a seed of this supermassive black hole, and it takes a shortcut to become a star. Obviously, it is not immediate. It has to go through the collapse of the star, and the fusion process, hydrogen, helium, carbon, iron, all that has to happen, and then a stage will come when it cannot hold on and it collapses on its own. But when it collapses, it is 4 million solar masses, equivalent mass, falling on itself, and suddenly you have a supermassive black hole in the ancient universe, and other parts of the galaxies are also forming. So that is the second part of